Now that we know what a game is, let's speak about how to reason about it. We'll be speaking about something called solution concepts. Solution concepts such as the most famous of them being the Nash equilibrium. We'll be first speaking about something called dominance. But let's first speak about what a solution concept is in general. A solution concept embodies a principle of rationality. So we're looking at rational players, and in game theory, rationality tends to mean maximizing expected utility. This is not unique to game theory. Decision theory, which can be viewed as single agent game theory, adopts the same perspective. The idea is we have the agent has some assessment of how likely different situations are. It has different preferences for different situations, and it takes actions that in their estimate maximize their expected utility. That is, actions that lead to situations whose product of probability and utility is maximal from the agent's point of view. In general, for when you have a single agent, that is not conceptually problematic. But when we have multiple agents, which is the stuff of game theory, things get interesting because let's think about it. When I think about what might be the case, well, that depends on what other people do. And what other people do depends on what they think might be the case, which in turn depends on their estimate of what I will do. So we have these beliefs intertwined, and that's what makes life interesting. So we'll be looking at several solution concepts. We'll start with a relatively simple and relatively rare one called dominant strategies. Conceptually, a dominant strategy is something very straightforward. It's a strategy that's best for their agents no matter what other agents do. As we've just said, in general, what's best for me depends on what the other agents will do, but there are some cases where no matter what they do, I'm better off doing a particular action. Mathematically, it looks like this, and this is an opportunity to again get comfortable with the notation. So the utility for agent I and now let's remember, what is the argument to a utility function? It's a vector, the action by all agents. But here we break it up into two components. The action by the agent himself, him or herself, A sub I, and the actions of all the other agents. A sub I will always mean actions of all agents except agent I. So what we are requiring in order for A sub I to be a dominant strategy, we require that for any other agent, any other action by the agent, the payoff for the agents when they take AI and the other agents take A sub I is always higher than if the agent were to switch to some other strategy, AI prime. And that, of course, has to hold for no matter what other agents do and for any other strategy the agent might consider. So no matter what the other agents do, I'm better off doing AI rather than anything else I might do. We say this is weakly dominant because we're looking at greater than and equal to. If we look at strictly greater than, then we get the notion of strict dominance. So that's a very natural notion to consider, and let's see it in practice. Let's go back to our favorite example, our predator-prey example. Thinking from the perspective of the predator now, notice that the predator has a dominant strategy of being active. Because, let's think about it, if the prey is active, then of course the predator would rather be active rather than passive because they'd get 1.7 rather than 1.6. And similarly, if the prey is passive, they'd rather be active because they'd get 3 rather than 0. So either way, being active is better, and being passive for the predator is a strictly dominated strategy. Notice also that once the dominated strategy is eliminated, the prey now has a unique kind of best response, which is to be active. and therefore active-active is the unique outcome according to this principle of eliminating dominated strategies. Notice, by the way, that the prey, does not have a dominant strategy. It only has a unique best response to the dominant strategy of the predator. Contrast this with the next game, which is perhaps the most famous game in game theory, called Prisoner's Dilemma. The story goes like this. Two prisoners have been captured, and they are given the opportunity to do one of two things. They can each either confess to the crime or deny it and remain silent. If they both remain silent, then they get some moderate punishment of -1. If, on the other hand, they both confess, then they get the most severe punishment of -4. If, in the most extreme case, one of them confesses and the other one denies, then the confessor gets completely off the hook, whereas the denier, the person who remains silent, gets the most severe punishment of -5. On the face of it, a very straightforward game, but notice what happens here. If you look at it from either player's perspective, but let's say in this case the role player has the dominant strategy of confessing, because in one case they would get a payoff of -4 rather than -5 if the other player confessed, and if the other player remained silent, they would get a payoff of 0 rather than -1. So either case, they're better off confessing. And of course, this is a symmetric game, and therefore the only kind of outcome, the dominant strategy outcome of the game is for both of them to confess and get a -4. This is of course paradoxical, because had they only cooperated and remained silent, they would have gotten a much better payoff of -1. And so this is one reason the game is famous, because of this paradoxical nature. Let's look, this is a case of strict dominance. Let's look at another case of weak dominance. So here's a game with a weakly dominant strategy. This is a game where there are two players. They can each decide either to go to the movie or stay home. If one of them goes to the movie, the other person definitely would like to join, much better than being home alone. But if the other player stays home, then the second player is indifferent whether they go to the movie and are lonely there, or stay home with their friend but don't see a movie. They're indifferent among these two options. So what is the situation here? Here again we have a dominant strategy. The strategy of going to the movie is dominant. And why is that? Well, let's think about it from the role player's point of view. If the column player goes to the movie, then they've got 1 minus 0. It's definitely a better outcome. If the other player, the column player, stays home, then they get, in both cases, 0. They're no worse off. And since this is equality here, we get a weak dominance, not strict dominance.